Hey guys, so today we are going to move on to part 2 of our lesson this week. So we are on 1.2 and we are talking about dilations. Dilations are when you take a shape and make it bigger or smaller. We're not changing the size or the shape. Oh, we are changing the size. We're changing the size, but we're not changing the shape or the angle measures or the actual orientation. That's what I was trying to think of the word. So the definition of a dilation is to grow or shrink. Zooming in on something, that is a dilation. Zooming out on something, also a dilation. So that's kind of what we're going off of today. That's where we're starting. Feel free to click our link here and it'll bring you to a website called Virtual Nerd. That being said, dilation, again, growing or shrinking a shape, keeping the shape's integrity. All right, so it is often a change in position. When you dilate something on a graph, it does tend to change its position because you can do it on a graph and you can do it off of a graph. Doing it off of a graph, I could just say, okay, you double every side length and it doubles the shape. On a graph, it's going to move it a little bit. So it does change position when done on a graph. It is a change in size, not orientation. Remember from our earlier videos, orientation is when the shape itself moves around and wobbles. It's facing a different direction. This next part, figures are not isometric or congruent. This triangle, if I dilate it to this triangle, is no longer the exact same triangle. It makes it bigger. Therefore, it is not a mirror image. It is not exact. It is not isometric. Our next part, figures are proportional or similar. Sorry, they're proportional. You guys should have heard of that before. Proportional means that they get smaller or larger in a proportional manner. So say you're working on, it took me a while. So if I have A over B equals C over D, I know the different proportional relationships at play here. I know that A multiplied by something will get me C, and I know that B multiplied by something gets me D. There's some variable, K, that we are multiplying by in a proportion to get the missing number. So that K is something called the constant of proportionality, or our scale factor. That is how big you're making it or how small you're making it. This is a pretty funky example because I'm looking at a fraction. If we talk about proportionality amongst money, we can say that 100 pennies is the same as $1. So in order to get from 100 pennies to $1, I would have to multiply by 1 over 100 because that is our scale factor. That is how much of an emphasis we're putting on the price in order to make it equivalent. So, that being said, that scale factor is the key to dilations and is the key to anything proportional. A lot of you guys learned it as slope once you get to graphing lines. All of that essentially is the same thing. It's how far you're going every one unit in order to keep it relational. So the interesting part about this is if you take this figure and you grow it or shrink it, the angle sizes stay the same for any shape. It doesn't have to be a triangle. I just like using triangles because we're going to see them a lot this year. And I like using triangles because it makes it easier to graph. But we will be graphing a rectangle together, I think. Maybe. We'll see. So we have this triangle, and if I'm growing it up, blowing it up, it's going to get really big. But those angle sizes are going to stay the same. The size of that line might double or triple. Does that make sense? So the lines are going to increase at a proportional rate, which means if one side is doubling, the other side is doubling. If one side's getting cut in half, the other side is getting cut in half. So they're growing and shrinking at a proportional rate, but those angle measures, all those little angle bits, are staying the same. They're the same triangle, different sizes. So they're no longer equivalent or isometric or congruent. Now we would classify this as proportional or similar. They're similar triangles because they do share some stuff in common, but they're not the same triangle. We're not trying to prove that they are the same triangle, which is another thing we'll get to this year. So now we are looking at, it is centered at 0, 0. That is kind of the point that we go back to kind of make our big lines. It'll make sense in a little bit. And then it increases or decreases by a scale factor. That is what I talked about earlier. That is that key number that we're multiplying by. So you are going to multiply your scale factor to every parts, or to all the parts of every coordinate. You are multiplying that scale factor to an x and to a y. So whatever you have, if your point is at 1, 1, and you are multiplying it by a scale factor of 3, you're going to say 1 times 3 is 3, 1 times 3 is 3. That point is now at 3, 3. This is a graphical way, an algebraic way as well, to increase the size of something on a graph. So bear with me and we will go through a couple examples together. So I did include another video on scale factor, and what that is, we typically see it as the variable k. Because a long time ago, a bunch of mathematicians kind of picked letters, pretty common letters for things. That's why we have an x-axis, a y-axis. It really doesn't matter what we call it, so long as we're all on the same page and we know that this is x and this is y. Same kind of thing. Scale factor is typically denoted with a k. So here I have, if your k is greater than 1, the shape will grow. If the k is smaller than 1, the shape will overall shrink. Ed, what numbers do we know that are in between 0 and 1? Fractions. If k is a fraction or a decimal, it's going to be smaller. If it is a mixed fraction, if it's like 2.5, then you're getting bigger by 2.5, as opposed to if you're just multiplying it by a half. Because remember, like if you're taking half of something, well, if you have 5 of something, you'd multiply it by 5. If you're taking half of something, you're multiplying it by half. So again, that k less than 1 is telling us it's going to shrink. So now we're on to the rule. What exactly do you need to do? Well, like I mentioned, you take your x and your y, ignore that, that's not a negative, that's just like a little dash that inputted that I didn't get rid of. We have our x and our y, and now you have k times x and k times y. K remains the same for all coordinates. So for this, It says dilate the pre-image by a scale factor of 2. I'm gonna zoom in here to kind of show this one off a little bit better. I'll try it. We'll see. So, shapes, I'm gonna come here and I'm going to actually input little dots. I know my image is, or my A is at 1, 1. So I'm gonna multiply 1 by 2 and get 2. And I'm gonna multiply 1 by 2 and get 2. So my point A prime is now at that dot right there. B prime is at 5, 1. So 5 times 2 is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not going to have enough room for this shape on this graph. Not great. And then 1 multiplied by 2 is 2. So that dot right here is B prime. So I have A prime, B prime, and C prime is going to be way up here, and it's not going to fit. So let's plot it anyway. All right, so 1 times 2 is 2. 2 times 2 is 2. 1 times 2 is 1. Yeah, still 2. Oh, yeah, I was right. 1 times 2 is 2. 7 times 2 is 14. So I'm going to count up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 is going to be at the very, very tippy top of this page. So now, in order to show the dilation, I'm going to put that here. Anyway, so now we have, I don't know why it snaps up like that, our shape, our original shape, and then we have A prime, B prime, C prime. Working things on this graph is not going to be perfect. Things don't automatically snap to this grid, and that is perfectly fine. It doesn't need to. It just needs to give you kind of an idea. If you would rather doodle on this page, if you want to print this out and doodle on it yourself, by all means, have at it. Gonna see if I can make that fade in. I'm not gonna play with it too much. All right, so there we have our dilation. I took my x value and multiplied it by my scale factor. And notice that they're not lined up anymore, and that's what I kind of meant by our scale factor. It's gonna like continually grow off of this point right here. So if I were to take lines and connect those two, I'm gonna have all the points in between and further on, if I continue that line, that show me where this should be, like A. All of our A's, if I were to do this again with an even bigger version, it would be at A, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and it would continue growing in that way, which I find kind of interesting, but that's me. I'm a huge nerd. So yeah, that is our dilations. And again, if you don't appreciate, if you don't want to use the notebook, by all means, I'm not making you use this notebook. I'm just asking that you make a copy of it to kind of keep on you, because it does have some really good resources and all the definitions and everything you would need.